Let's talk about the test. As soon as I start recording. So you got your grades. Did it show you the answers and everything or no?
Oh, that answer.
Let's talk about the test. Okay. Did anyone at home, did you see the answers? Hello? Hello? Can you see the screen? Can
Yeah, I
anyone-
can see the screen.
Oh, okay, good.
I couldn't see my answers on the test though. I'm not sure why.
Because I wanted to talk to you about it first, but then it told you what your score was, so that's fine. You shouldn't, it shouldn't have told you the score until I was done grading them. Okay, but I was gonna curve it a bit. So let me tell you what the grades were. There are 9 people in this class. There were 2 grades in the 80s. There were 5 grades in the 70s and 2 grades in the 40s. So if you think about because it was the first time I was doing it, it was very interesting to me. I learned some stuff because I don't usually watch all the videos, but it was super annoying, the instructions popping up all the time. Did you find that annoying?
I went into the first question. I just read the instructions.
I know somebody actually skipped it and wrote just okay because they missed the question. They breezed right over it. So I'm going to rearrange things for my other class and for the next test so it won't do that. But yes, it was annoying. I was there with you. I was feeling your pain. I was like, oh my God, this is horrible.
And then as soon as I realized there was a question, I remembered I was like, oh my God, he's grading me on how quick I can do this.
I know there were very few people that pissed me off. In this class, nobody pissed me off for taking time. I don't think I took off any points for being slow. The other class though, definitely. There were definitely people who looked at the question, mumbled the wrong answer, and then later on got the right answer, and I took off points anyway. Because you need to be able to answer these quickly, not muddled and not like unsure of yourself, but you're mostly sure of yourself, bless you. Okay, mostly they were good. Okay, so I don't remember taking off any points for people being like, and some of you stumbled and changed your mind or whatever, but that was still fine. If I was interviewing you and I said, what is math? And you said, math is a study of change. Oh no, that's calculus. Math is a language. That would be fine in an interview. But what wasn't fine is that all of the people putting themselves down. Oh my God, it was so depressing. You had the right answer, and I'm like, yay, I'm ready to give points. I think this is wrong. I'm backing out on the whatever. It's like, no, I'm giving you the points anyway. Why are you backing out? So there was an awful lot of self-doubt when there didn't have to be. Okay, so you know who you are. One problem is I feel badly that I told you guys the thing about cheating because I have to check the room scans. And then I was like, well, if you're room scanning it, I'm just encouraging you to cheat. So I have to decide what you guys have to tell me how much you actually need or use notes other than you know, because it seemed to me that, as I said, in the other class, I think those other people, I didn't tell them they could have notes, but I think they had notes and they had the wrong answer at first. And then they looked around for it, found the right answer, but it didn't matter because I took off points anyway. So if the notes are going to eat up time, I've had open note tests and I didn't like them because they ate up a lot of time looking for answers. And then it wasn't that those questions I lost points on, it was the other questions I couldn't get to. Because I wasted too much time looking around for something simple. Okay. All right. What else? I think I was about the test. So they weren't bad, and I was kind of happy. As I said, I'll next time it won't be like that, where you have to read all those instructions every time. I just wanted to make sure y'all knew which ones to say. And so some people did this too. They typed before they wrote. And that was wrong. They spoke before they spoke. sorry, they wrote before they spoke, and I'm like, no, you have to say the answer first, and then you can type it down. The other thing the room scans were all terrible. Everybody screwed up the room scan. You're supposed to slowly move it around so I can see the whole area, and you're actually supposed to show under the desk, which I don't think anybody did.
Say that.
It says it in those 20,000 instructions that you're supposed to read, and or even on the syllabus, it says it to do it slowly and whatever. It doesn't say, yeah. Anyway, you're supposed to scan the area so it looks nice, but I don't know. Let me think about it some more. But I didn't mind the speaking. It wasn't that hard to grade. You guys were mostly pretty good, and I feel like I like you more now than just grading a paper with just, having heard you talk and seeing you muddle through the problems and stuff. That was fun. Okay. I think if you're keeping up with the material, the material, this format will be good for you. But if you're not paying attention in class, like the people that really screwed up in my other class were just not coming to class. They weren't here, they weren't paying attention, and they really screwed up. Now, I don't know what happened with the people who got 40s. If you got a 40, you want to talk to me after class, we can talk, but I wasn't that worried. Oh, I know where people who got 40s lost a lot of points on those questions, the reading comprehension questions. Like I have to look at the data on that. I can do that right now, actually. I shouldn't do that right now. I have stuff to do. Question, not the first three, not the second three, but the third set of three.
Like the actual.
The multiple choice, the ones that were multiple choice ones? No, the ones that were literally multiple choice. Like what happened here? Those questions. You missed that. There's no partial credit. I can't give any partial credit for it because it's either all or nothing. And so some people missed all of them. And that would have been 18 points right there. And I don't know why. Okay. But anyway, I will go through in Mod 5 and I will look at the I will do an item analysis on the test. But since I'm probably next week, I'll do an item analysis or closer to the midterm so that we can review it for the midterm, unless you want to go over it at some point. But I need to go over Mod 6 because there was stuff in Mod 5 we didn't finish. Yes. I went over the homework and stuff, but there was topics I was supposed to go over. What?
Like,
How am I going to cover it? Like probably 10 points, maybe. Since somebody got an 88, I can't curve it much higher than that. That makes all those 70s like Bs. And it's not that I'm giving Bs away. It's that we're trying this test for the first day. You were my first guinea pigs. And I don't want you to be hurt by the fact that I don't know how the test is going to work out. But the next tests it will be the same. I'm just going to do the same thing on the next test. Once I set a thing to do, that's what we do. Okay. What is growing here? It's too big. Okay. Let's see. Okay, so what's due today on the 8th is the mean value theorem discussion and quiz 5. So let's look at quiz 5 and see how you did. Also the topics, let me just, while I'm here, the things we didn't talk about so much were inverse differentials and error. And today I'm supposed to do L'Hopital's rule and zero. I can do all of that today. I can. Yeah. Okay. Let's take a look at how you did on quiz 5. You all take quiz 5. Okay, worst question. Okay. So this is one of my favorite questions. It says use local linear approximation to find the square root of a function. And they don't, it's randomly generated for everybody. Okay. They give you a formula. So let me copy this down. I love this question. For sure, you're going to have this question because it's my favorite question. I should say for sure, but it's one of my favorite questions. Use a local input to find the square root of center 8. So pick a number near 9. 8. Fine. So to do a local linear approximation, you have to do the tangent line. I watched during the test, there were people who were saying, I know that tangent line is in here, and it is. It's this one right here. That's the tangent line formula. Okay? It looks just like a line. It has to look like a line. Okay, it's a line, it's the function plus the derivative of the function times how many derivatives. So in other words, how many derivatives you're going away from the function. So 8 is 1 away from 9. So you're going to evaluate the function at 9, and then you're going to add to it every derivative, which is the slope of the tangent line, times the distance, how many times you are away from 9. So let me do this into f of x equals square root of x. So here's what I'm saying. So at 9, let's see, what's wrong with this? Oh, here, put 9 in there. Just put a 9 in there. You can see there's the tangent line right there at 9. So in order to do 8, we're doing the slope of that line and we're going backwards by 1. So if you're going backwards by 1, you're going down the slope by 1. So literally when you plug 8 in there, you're saying I'm doing minus 1 of these derivatives. Okay, and then I'm going to add it to whatever the function was at 9. Okay, so I can't do it that way. I'll do it this way. I'll just do L of 8. I copied it and pasted it instead of flipping. Hold on, I'm just going to delete it. Where was it? Okay. So anyway, that's the answer. So I take the local linear approximation, the function, I'm doing it at 9. I'm taking the derivative at 9, and I'm doing that many 9s away. Or that many derivatives away. So if you had said 11 or 13, I just put a 13 in there. And what's it doing? It's saying, okay, f of 9 is going to be the square root of 9. What's the square root of 9? 3. So that's going to be 3. So let me just do these parts one at a time. So this is going to be 3, because the square root of 8 is something like 3. And then what's the derivative at 9? When you take the derivative, and you evaluate it at 9, and you end up getting 1/6. So this derivative right here is the slope of that line is 1/6. That's the slope of that black line there. Was read before. Okay. So again, when you put an 8 in there, it's saying, I'm taking 3 and I'm subtracting a 6 from it. When you put a 13 in there, you're saying, I'm taking that 3 and I'm adding 4/6 to it. Okay, that's what it means, because you're following that black line instead of, why is the black? Oh, you're following this black line instead of the blue curve. That's what it means to be a local linear approximation. Okay. Any questions on that? I think on the test, it just asked you to find the equation of the tangent line. And for that, you would have to do what I just did. Plug those things in and you can get the equation of the tangent line. All right, another one. You'll notice that this one's a formula generated into whatever you got for A. It subtracts 9 from it, divides it by 6, and adds 3. So that's the formula for all the answers. Don't memorize that formula, though. But it was really easy to just plug it into decimals. Especially if I say user center of 16 or something, then you have to change it. Formula is different. Okay, here's another one. There's the formula right there. It says a car. Okay, so this is a related rate problem. You have a car traveling. Just car is traveling. I'm going to delete these guys here. Okay, so this is what the problem says. It's a word problem. It's a related rate. A car is traveling at, give me a number. Showing really 3 kilometers. Let me get 30 kilometers an hour. Okay, that's still pretty slow. And it's at a point that is how many kilometers north? Give me a small number. 10 kilometers north. That's pretty far to be away from a cop car. Let me get 0.3. So you don't listen to anything I say. Why do you? What? Okay, kilometers. Okay, a police car is traveling at. Give me a speed that a car would be traveling at. Police car. 60. Sure. Oh, you listen to what she says. Okay, the other point is given you is 0.25. All right. So it says, what's the distance between them? So this is one that comes from this x squared plus y squared from the Pythagorean theorem equals z squared. And if you take the derivative with respect to time, oops. And so I want to take the derivative with respect to time. So put it here, d dt. So if I take the derivative with respect to time of all of these, by the way, this looks a lot like that exam question that some of you had. So what's the derivative of x squared? To what? Times what? D x dt. Because it's related, right? The variables don't match. Okay, none of the variables will match. So what's the next one going to be? Plus 2y dt equals 2 c dz dt. Okay, dz dt is what they're looking for. Okay. Yeah. Going back to that formula that we had x squared plus y squared equals z squared, x squared plus y squared equals z squared. If I solve for z, so I'm just going to solve for z, and that's going to be z equals the square root of x squared plus y squared. Okay. Wow, that's awesome. I think I broke decimals. What's going on over there? Okay. Well, anyway, I'm going to take this and I'm going to put it in for z. That. So now I have x, I have y, and I have dx and dy dz. So now all I have to do is take that information from the equation. What's 30? Is that what is that? A rate or value? It's a rate. So let's say that's dx dt. So we'll put that in for, let me just copy this over here. We'll call that dx dt. Dx dt, I'll put in as 30. Okay. And what's the other thing? And what's 0.3? Is that a rate or a value? Is the value, which value is it? X or Y? It's X because just because I said 30 was. And then I'm going to put that in here too. Okay. What's the other one? Y is, okay, 65, rate or value, is it dy dt or y? So rate 65, and then what's the other one, 0.25? Which one's that? Y is the only one that's left. Okay. Now, Desmos will solve for something. What's dy dt again? 65. Did I do everything right here? Everything is filled in. To get it to solve for dz dt, I just put an x there. And then it should solve it. The answer should be here. There it is. The answer is 64.65. Okay. Does everyone understand that? I have to put the x in to solve, have Desmos solve it like it was an equation. But really, I'm just solving for that dz dt when I plugged everything else in. Okay.
So you said that we have to change the DZ over to T to it. So that
To get Desmos to solve it, because it doesn't know how to solve for dz. It doesn't know what the hell you're talking about. But it does know that if you put an x there, it'll certainly graph it. You can put a y in there and it'll graph a horizontal line. If I put a y there, it'll graph a horizontal line. Same thing, give me a horizontal answer. I'm just making a graph. So I'm not really solving it. It's not solving. Desmos tries to graph whatever equation you give it. And so if you give it an equation with an x or y in it, it'll give you a vertical line or a horizontal line. Does that make sense? It doesn't matter. But if I put a z in there, it won't do anything because this is, unless you're using the three-dimensional stuff and there's a z-axis. There is no such thing, so forget about it. But x would tell you the equation of that, this is x equals 64.65, that's the answer. So all of this boils down to x equals 64, because that's what Desmos is trying to do, is trying to graph that. Okay? Sometimes you have to put a minus in instead of an equals to get it to give you that x-intercept. If I put a minus there, then you have to look for the x-intercept. Okay? Desmos doesn't like giving you answers, but I don't care, get the answer out here. Okay? Questions on that? So did you see this formula right here? That's the formula. It's just students remember the a times b plus c times 0.25 because the 2.5 is given over the square root of b plus 0.25. Right. And that's it. Doesn't matter, they're the same form. When you know that's the only thing you're given on Desmos. Extra plus one, it's somewhere in this, or somewhere in here, there it is. That's it. So students memorize this because they know it's coming. They know it's coming. But you know the mistake that I did it this way because just in case you don't know, but this is what students do when they memorize the formula. They think the formula is this. X prime plus y prime. Yeah, the twos don't matter. It's fine. You can get the twos, all the twos cancel out. In that equation, they all cancel out. Divided by, this is what they do wrong. They know it's a square root and then they do x plus y. That's what they do, and it's wrong because that's square. If you're using a quadratic formula, this has to be squared. And this one has to be squared. So that's okay. This formula is okay. This is what they memorize. I know because I see them type it in. Okay, you're allowed to memorize this. That is not cheating to memorize this formula, in my opinion. Starting from scratch and doing it, that's impressive. On these questions, you have all the time you need, so you can. Like, I don't think anyone took an hour to finish that test. What did you take? 30 minutes, most of them between 30 and 50 minutes. Because you have to answer those questions, the ones have to be done quickly at the beginning. And the rest, some of them are pretty easy. The reading comprehension ones are easy. Okay. They're not easy, they're just, you can look at them all day, they're not going to change. All right. this is. Okay, so this one is a distance traveled on turnpike according to the bike registration between the second and fourth as the mean value says, oh, this is a mean value theorem problem. Ooh. How do we do that? So, this one has between the second and fourth hour. So they're telling you second and fourth hours, okay? Okay. So let's go in here. And we'll just go down to the bottom. And we'll put in the problem. Ticket from the police says according to the what regression is this? Ooh, this is not a quartic, it's a what? Cubic regression. According to the cubic regression. Between the second and fourth hours, the mean value theorem says your speed was blank at hour blank. Okay, so second and fourth hours. Okay, those must be these two endpoints. Second and fourth. Now, what is this going to give us if we turn it on? That'll give us the 110. That's your average rate of change is 110 miles per hour. And when was that equal to your instantaneous? So this is your derivative. So when are they equal to each other? When is the green and the blue line equal to each other? There's one of them. The green line is the derivative or the instantaneous rate of change, both. Okay, so which of these answers do I want? 0.08 or 3.11? The mean value theorem doesn't only applies for certain things. You're on the turnpike between miles what? 2 and 4. So it has to be 3.1. That's the answer that you're looking for. And if you check it, if you just take the derivative, f prime of that number, you see that they're the same. So according to the cubic regression, your speed was what? 110 miles per hour. Wow. 110 miles per hour. And it happens when? At hour 3.1, hour 3, whatever. We're at hour 3. Okay. All right. That's the mean value theorem problem. Oh, here it asks for it to 1 decimal place. So 3.1 and 110.4. Okay. Any questions on that? Oh, you know what? I apologize on that test. Another thing that I saw, you know, the one where I said f of something and f prime of something and f double prime of something, and I said say it as a speaker. Some people said it as a writer because it was set up so nicely for saying it as a writer. Like they said, f of 2 equals this, and f of 2. Yeah, I had 2, but not a lot. There's so many points on those questions. I couldn't take off a lot of points because they did everything else right. But yeah, say it like a speaker is different than say it as a writer. And one of them, the limit one, was say it as a writer, and some people were saying it as a speaker. Did you do that? You might have. It said the limit as x goes to 7, and it was nice because they sounded really good. Whoever it was who said it as a speaker said it great. It was like, according to this regression, as we approach the 7th hour, we can expect this. It's like, no, it was just supposed to be said the limit as x goes to 7 of f of x equals whatever. But I think it's getting there. All right, here's a problem. What happened here? What lines were those? 17 and 18. What happened here? Okay, so we didn't go over this last time, but it isn't that hard. You could tell me what happened. So the derivative of what? Inverse sine is all this crap, but then what's this then there's a cosine on the inside. See, there's an inside function. Then you take the derivative of the inside function, get minus sign. So what must that be? So it's a derivative of the inverse sine, and there is a what rule? No powers. What's this? When you have an inside function and you take the derivative of it, what rule does that? Let's look at the answers. Oh, look, chain rule only. That's the rule. There was no power rule, because there were no powers. There was no quotient rule. It came out as a fraction, but that's because of the derivative of the inverse sine. It wasn't a related rate. And it wasn't a related rate, and it wasn't a local linear approximation. So it was just the chain rule. I know we didn't get a chance to go over this, but if you have the derivative of the inverse sine, let me just do it this way. This is the derivative of the inverse sine. Okay, that's the derivative of the inverse sine. So there's nothing to do. That's just one of those things, it's like a quick and dirty rule. Okay, what this had going for it was there was something inside. There was a chain rule in there. So because there was a cosine in there, let's say if it was a tangent. That was a tangent, then this would be a tangent. You remember you have to leave the inside alone. And then what? What's the derivative of tangent? Secant squared. Okay, so that's just a chain rule, but the derivatives you have in there are tangent and inverse sine. Okay. By the way, I think if this is inverse cosine, just so you know, I think if it's inverse cosine, literally this is the difference. The inverse cosine has a minus, it's the negative of the inverse sine. Go figure. Anyway, questions on that? Let's see what else. 20 and 21, and 20 and 21, that's one. Okay, so now who wants to tell me this? I will pick on somebody at home. Hold on, people at home. By the way, I didn't take attendance from people at home, so you can't be disappearing on me. Suhave, are you there? Are you awake?
Yeah, I'm here.
Okay, Suhave, what exactly happened between lines 20 and 21?
I think I'm not too sure. I think maybe the quotient rule.
Nice guess, but no.
Sorry.
What? It looks like there's a fraction, so you think of quotient rule, but no, the inverse cosine has the fraction in it as an answer. Like the natural log would be 1 over x. Anyone want to stab at it at home? What do you think happened here between lines 20 and 21? Devon, Kara, Jake, Nana. What happened?
Was it the chain rule?
That's correct, Jake. It was just the chain rule, just like the one we just did. Literally, in fact, it looks exactly the same, doesn't it? So I changed the sign to a cosine. Remember I said there'd be a minus difference, and there was. But you see there's a 9x to the 5th, and it's left alone. And then there's times 45x to the 4th is just a derivative. Okay. That one wasn't so bad. Okay, so this is 23 and 24. Let's see about 23 and 24. Okay. All right. 23, 24. Who wants to take a stab at this? Anyone here? Anyone at home? No, it isn't. It's totally different.
It's like,
It's that rule.
where it's like n to the power of x.
Yes, it has a name. It's with a P. Rhymes with hour. No, rhymes with hour. It's the power rule. You bring the 9 down and you subtract 1 from it. Yes. Do you see that? I brought the 9 down, but you see there's a thing on the inside. So they leave the inside alone, right? Do you see it being left alone? The 9 is coming down with the front. The inside is being left alone, and then you're subtracting 1, that's 8. That's the power rule, and then what's all this crap right here? What do you think it is?
The inverse of secant.
The derivative of the inverse of secant. That's derivative, that's inverse secant, that must be the derivative. No. I just put it here for fun. I didn't ask you to memorize the derivative of the inverse secant, but you can see it's a power rule, and the only way for this to be the derivative of that is if that's the derivative of the inverse secant. If you want to check it, you can always do this. You can just have it graph both of them. Have it graph not the inverse, but the derivative. Have it graph this. Okay, you with me on here? That's what the derivative of inverse secant looks like. And this is what I think it is. And they're the same thing. See that? That's the best thing you can get Desmos to do, is to see if the derivative that you think it is the same thing. If you didn't think it was, if you thought it was something else, thought there was a 2 in there, it wouldn't look the same like that. Okay, if it in any way looks different, it is not the same. All right, next one. So this was a power and chain rule. Okay, as opposed to just a chain rule only. It's a power and chain. Okay. Say this. What's up with saying these things? How do you say that? Somebody at home say it so everyone can hear it. Kara, say that. Kara? Kara, are you there?
Yes, I'm here, but it's a little tiny on the screen.
Oh, then let me make it bigger for you.
I'm sorry.
No, it's okay. I'm gonna make it
I
bigger.
can't tell if that's T.
I'm making it bigger.
Oh,
It's a
T.
T. That little thing is a T.
Oh, okay. Thank you. I couldn't
looks-
see that.
I know it looks okay, so what is this?
1 over X
Yes.
and well, for sure. I'm not sure how to say, is it D to the, like, is it a derivative of T
No, it's the derivative of X.
of X?
With respect to T.
Oh, okay.
It's a related rate. This is, you're taking the derivative with respect to a different variable. It's related. You do that. Was that what you were gonna say?
I was gonna ask, so it has to go under, there would be, because wasn't there, like, I don't know, I vaguely remember there being an example where it was like in parentheses. Oh no, that was evaluated at,
That's evaluated at.
so if it's being with respect to type.
Yes. You wouldn't want to, so you wouldn't want to use that notation here. She's thinking of this. Let me see if I can write it. You wouldn't want to say capital D with a little t, and then use a parentheses like that, because that would imply that you're saying t equals 2. But if you want to take the derivative with respect to x, and then evaluate it at x equals 2, that would even be hard, because you're taking the derivative with respect to t. Time. It's another variable. That's the whole point with the related rates. You're not taking, the derivatives are not. Here's how it's said. When you're talking about you're talking about y and x, you take dy dx, you're saying, how is y changing as x changes? So as y is changing, or as x is changing, y is changing. So if you have a very steep slope and the derivative is very big, when x changes a little bit, y changes a lot. When you have a very narrow, when you have a very flat slope, when x changes a lot, y changes very little. That's x and y. When you're talking related rate, you're now talking about the x is changing a certain, like it's changing at a certain rate. So you're moving along the x-axis at a certain speed. So how fast is the y changing? If the x is changing, if you're moving around the if you're moving slowly on the x-axis, then the y is going to be changing. Even if it's very steep, it's going to be changing slowly. But if you're moving fast along an x-axis and you have a steep slope, then the y is changing even faster. So the derivative, so the how y is changing depends on the derivative and how fast the x is changing. That's what we're going to be talking about with respect to error soon. That's what I was supposed to talk about last time. Okay. All right. Let me see. Let me see how many more of these I have to do. By the way, on the test, there were lots of people said things because it wasn't multiple choice. Sometimes people said things differently, but correctly. If what you're saying matches what's written, I don't care. If it's correct. Okay. So some people insisted on putting quote parentheses and calling them quantity and end quantity because I do that, but you don't have to do that. It's just a function of x. You can just say f of x. You don't have to say f quantity, x, and quantity. You can, just don't have to. Okay. I just say this. Somebody at home want to say this? Anyone? I'm going to find somebody then. Davon. Say it.
The derivative of the inverse tangent of x equals 1 over 1 plus x squared.
That's where you have to say the quantity, 1 plus x. You should say 1 over quantity, 1%, even if it doesn't say it here.
Okay.
You should say, 1 over the quantity, 1 plus, here it is, over the quantity x squared plus 1, and quantity, you should say. Okay, it's fine. You did a good job. But what you need to be able to say inverse tangent and not say tangent to the -1. Okay. All right. Next one. These are all still, okay, this is a 16%er. Somebody got this one. The please drop, somebody got it. 50%. What are some applications of derivatives? What have we done with derivatives? We've applied them. Do you know where? They were Newton's method. Related rates.
Average rate of change.
No, that's the question to throw you off. We did average rate of change is not an application of derivatives. Derivatives might have come from average rate of change, but not that the other way around. Okay. Related rates, Newton's method, local linear, and we haven't done L'Hopital's rule or error. We're going to do that. Okay. And these are other answers to those questions. What is finding a tangent line that is centered near a desired value? What is that? That's one of the things that's on that list right there. One of these is finding a tangent line that is centered near a desired value and approximating something with it.
Is it Newton's?
It's the local linear one.
Um,
Remember that was the square root of 9 that I did at the beginning. Find a tangent line near center to find a desired value. Okay. The derivative of the outside, leave the inside alone, multiply by the derivative of the inside. What's that? It's an easy one. It's an old one. Which rule? It's not the power rule. No,
That's
It
the
is.
chain rule.
it's a chain rule. Thank you, Anuja. It's a chain rule. Implicit differentiate a main idea with respect to time. Which one is that? So you have a main idea and you take the derivative with respect to time of everything like we did before. Which one of those rules is it? The one with the cup. It's not local linear. It's not Newton's method. It's related rates. Yep. Okay, find the zeros of an equation. I skipped one. What finds the zeros of an equation? Newton's method. And then this one right here, switch the x and y, restore the function, and then use implicit differentiation. It's not one of these. But it's used. I'll just very quickly show you what that is, because I was supposed to cover it last time and I didn't. Back into it in my notes. Anyway, that's how you find the derivative of an inverse function. You switch the x and y's. All right. Because that's what inverses do. They switch the x and y's. All right. What is local linear approximation? Oh, that's 100% though. All right. So we're done with that quiz. So we've covered all the questions that people didn't get on those quizzes. Let me go back to lessons. Do I what?
Spider cells.
Why did I say Spider-Man? No. I changed that. Does that mean something I should know?
No, for some reason, a lot of the teachers wear like funny socks.
I wear not funny socks. Just very plain. What I do wear is funny t-shirts that you don't see. Because when I leave, I peel the shirts. The first thing I do is peel off this dress shirt because I hate them. And then I just have like a t-shirt on underneath. And so you can always see a little color underneath my shirt. A colored shirt. What? Nah, I'm not that cool. Not that cool. But the socks, I don't have any interesting socks. Somebody gave me interesting socks. I think I threw them away. Okay. All right. I'm trying to get it to mod 0. Where's mod 0? Okay, so let's flip here. I'm in mod 0. Let me just talk about the things I was supposed to talk about last time. Inverses, differentials, and error. Okay. So let me just, I can take attendance, so I do this week. All right, what is math?
Yeah, I'm asking everyone.
No, I'm going to,
A language.
yes, thank you. Thank you, Javon. And pre-calculus is what? Study of functions. And calculus is the study of what?
Change.
Of what? Functions. What are the two rates of change? How do we get from 2 points to 1? No. How did we take the 2 points of the average rate of change and make the 1 point of the instantaneous rate of change? We invented something. No, begins with an L. Limits. We invented limits. And then that gave us the instantaneous rate of change. What is the meaning of velocity? It's that. It has a lot of meanings.
It's,
One of them is rate of change, the slope of the what? Tangent line, which is the velocity, which is the first derivative. The instantaneous rate of change, yes. All of those things mean velocity. What applications have we done with derivatives? Well, we did, see there, the velocity is derivative, incidence of the tangent line. We did Newton's method, we did local linear, we did related rates, but we also derivatives of inverses. So I told you, all I did was tell you about them. But the way they were found is this. If you have y equals the inverse sine of x, and you want the derivative, so you want dy dx. So this is what you do. Since it's an inverse, you switch the x's and y's and get rid of the inverse. So that right there, that equation becomes x equals the sine of y. Does everyone understand that? You're moving the sign to the other side. That's what it means. Inverse switches x and y. So if you want them back, you just you switch the x and y's back. Okay, so x equals the sine of y. So now you have an equation with a y in it. So what type of differentiation can you use, Melanie? If you don't have it explicit, you use what differentiation? I know I asked you this question before. That's something I was asking you. Yes, implicit differentiation. You're implying it. So you use implicit differentiation to take the derivative of both sides. So you take the derivative of the one side, derivative of x is what? 1. Derivative of the sine of y. Now it's a what rule? You have a y on the inside, you have a function on the inside. The derivative of sine is cosine. Leave the inside alone. And then take the derivative of the inside. And that's what we're looking for, y prime, right? So I can just bring the cosine of y together. So y prime is 1 over the cosine of y. Well, that's not great. Because you can't say the derivative of y is 1 over the cosine of y because it's a function of x, right? We went an x in there. So you have to go back to SOHCAHTOA and start with the original problem, this problem. X equals the sine of y. Start there. And that means x over 1 is the sine. Remember, x is opposite and sine 1 would be the hypotenuse. And what?
So, not like this one over implicit differentiation.
Yeah.
We don't use that and we use SOHCAHTOA.
No, we just did implicit differentiation, but our answer had a y in the answer. You know how sometimes you do implicit differentiation, it has y's in it instead of x's? I can't have that.
So we should not use that.
No, we did use that. We had to do that. You have to use implicit differentiation. But now we're like, I need to find a way to get x's in there. So again, you're not doing this. This is some genius somewhere in the 1400s that decided to do this. You just know that this is how it was done. It was done. Implicit differentiation was switching of the x and y's was done. Implicit differentiation was done. Answer has a y in it. Answer needs an x in it. So we go back to this equation with the x equals the sine of y, and we use SOHCAHTOA. We say sine of y is x over 1, because there's no 1 there, so just put it in there. So we know opposite is hypotenuse, so it means this little triangle. The opposite is x, the hypotenuse is 1, and then we use this. So what else is done? So SOHCAHTOA's done. Let's just put another thing on the list. What is the theorem that relates these things? The Pythagorean theorem says that. It's not even on here. Oh, Pythagorean theorem says x squared plus y. So x squared plus y squared equals 1 squared. So you can figure out what that y is. It's just the square root of 1 minus x squared. That goes in here instead of cosine of y. Now we're using ka in SOHCAHTOA. Ka is adjacent of hypotenuse. Now that we have this, we do the adjacent, which is the square root of something and something, and hypotenuse is 1. So that's how we got this. Then we go back to this problem, which is y equals. It's just a lot. All I want you to do is say, wow, somebody was really smart. No, I'm not making you do this. Math people, magic. Professor Dumbledore and McGonagall, whatever it was. Back in the 1400s. Anyway, somebody came up with it. They used. We don't. We have critical thinking. We can analyze this. We can read. This is why I put that stuff on the test. I want you to read in comprehension. I want you to understand what was done. I wouldn't expect you to do it, but I would like you to see it and say, wow, okay, I can follow that one step at a time. And you have to understand these stories. People spend a lot of time making these stories. They got their doctorate in this 1400s, and probably in physics, doing this sort of stuff. And they were all excited. When they found one, they put it on the list. Ta-da! And that's what happened. It became on the list. And as things are discovered, they go on the list. Exactly. But you don't have to do that. The most I can hope for from you is that you understand how to follow, like you follow it. We learned these topics. We learned implicit differentiation, and so it was done. We learned SOHCAHTOA in pre-calculus and you forgot it, maybe, and it's okay. But you could refresh it if you wanted to, but you could understand it. And when you said, we just supposed to believe them? No, you're not supposed to just believe anybody for anything ever. That's the story of critical thinking. Don't believe them, but don't be like, oh, all right, I hate to be preachy on you. Critical thinking isn't doubting everything you hear. It's being smart about it. When someone says or does something that doesn't make sense, you're like, I don't know about that. And then you can look it up for yourself. And you believe things. Because sometimes I believe things that I read on the internet, and sometimes I don't. That's the one thing I have over you people who were born in the internet age. I don't believe everything I read on the internet because I had, before the internet, I had some idea of what was true and what wasn't true. But you read a lot of crap on the internet and you start thinking it's true. Deep fakes or what? Deep fakes all the time. Anyway, here's a derivative. Here's where you actually use that derivative of inverse sine. There's an inverse function. We went over this before, so okay. Here's something I haven't done yet. So here's a new topic. It's called differentials. And I also haven't created this week's say is how to say differentials. Ooh. But I didn't make them yet because I was too busy grading your tests, so I didn't make them. But it's really stupid and short. I said stupid short. It's really, there's not much to say with differentials. So differentials, why is it got crap in there? Huh. Differentials is another way of saying I'm taking the derivative with respect to nothing. You know how I said how is y changing as x changes? Well, guess what? Differential is, it's a derivative, but it's not with respect to anything. And what does that mean? It has to do with the fact that numbers themselves can be fuzzy. Okay, for example, if I said that there were 5,000 people at Mercer, do you think there are exactly 5,000 people at Mercer? No, I probably estimate, maybe there was 4,500. If I said 4,500, do you think there's exactly 4,500 people at Mercer? No. If I said 4,523 people, do you think that there's exactly 4,523 people? I'm giving you an exact number. If you're a science person, you realize that I gave you significant figures. I gave you all of the digits. So numbers themselves are fuzzy. And so therefore, an x value can be fuzzy. So when I was saying how x is changing, you just talk about how fuzzy the x are. It's like when you say the year, even when you're doing your project stuff, when you're saying the year 1950, talk about the beginning of the year, the exact 1950, the minute it started. Are you talking about the 50s, which would be a whole decade? Like, what are you saying? So every number comes with a little fuzziness. Okay, and so we describe that. So when you're taking derivatives, you take the derivative of x squared, you get 2x, right? When you take the derivative of y squared, you get 2y dy. Okay, we take related rates, 2y squared, you get 2y dy dt. Well, differential is not with respect to anything. So you say, see that dy squared? That's considered a differential, and it's equal to 2y dy. So you took the derivative with respect to nothing. Okay, and the way it's said, how do you say a differential? Literally just that. You say dy squared, 2y dy. You're just saying the letters d and y, d and x, but not that capital D. That capital D is for derivative. These are little d's. Okay, so let me go back to Desmos for a second. So when I get this done, a differential, that's a differential right there, dy. And how would you say it? Yeah, you just say dy equals the sine of x dx. Okay? You can't say them as words. Not to be confused with, oh, that was interesting. This one, that's another d. That's what? Oh, that's just one, but here. That's just the derivative of y with respect to x. Okay, but you don't say that as D. You say derivative. Okay, so you see that when you're saying D's, we assume in calculus you mean little d's as in the D in differentials. Okay? All right, so what does that mean to us? We're going to use differentials for something later on, but this is a slide ruler, by the way. Anyway, numbers are fuzzy in slide rules. That's how they work. Has anyone ever heard of a slide ruler? Anyone at home? Jacob, you ever heard of a slide ruler?
I have not, no.
Okay, well, so a slide ruler was used before calculators. Looks like this. Okay, and you literally, the inside, it's a ruler, like a ruler inside, and there's a little bar on the inside, and it slides. What?
You know when you go to the hair salon and you have to slide it? It's
Kind of like that, except yes, kind of like that. Anyway, what happens is there's this plastic line here, and if you want to multiply 2 times 2, you find the number 2 on the main bar, you find number 3 on the sliding bar, and you match them on top of each other, and then you look at the end, and it'll say like 6.
Do you have one?
No, this is before my time. I'm lucky that I even know how to use one. I had an ancient physics teacher who made us learn. He had a big one, like a 6-foot one. Mostly they're small, but they're little things. Anyway, you could go on YouTube and ask how to do it. It's no longer super rare. It's just rare to even know about it. But anyway, the numbers, if you start taking like 2, you take 2 and multiply it by like 1.54 something, it'll only give you approximate. It's the ruler. You have to, how you read a ruler, like that's how you read the answer. You get as many decimal places as the ruler can give you. The ruler is a really good ruler with lots of little notches. You get a good answer. If it's a cheap ruler, you're going to get not a good answer. So, oh, where was I here? So fuzzy numbers. If you say the number 1, that means plus or minus a half. So that's a big range. But if you say 1.0, that means everything from 1.05 to 0.95. Okay, it's half of this decimal, this last place. Okay, so 1.0 means 1.0 plus or minus 0.05. 1.00 is plus or minus 0.005. Okay, here's the population of Mercer. No, God, no. Totally made up. Don't know how many people are here, but the more digits you give, if you give that one 41.21, that's plus or minus half a person. Since you can't have half a person, it's pretty exact. But if you said 4,120, that would be plus or minus 5 people. 4,100 is plus or minus 50 people. 4,000 is plus or minus 500 people. Because if it was any more than 4,000, if it was 4,501, I would say 5,000. Okay. All right, differentials. So if you have f prime of x equals d f of dx, if you just don't take the derivative with respect to anything, you end up getting the differential. So you get d f of x equals, f prime of x times dx. Okay, that's what it means when you take the derivative with respect to nothing. So what does that mean for us? If what I was telling you before about if this derivative is steep, like it is in this black area, then a little wobbliness in x means a big wobbliness in y. If it's shallow, like it is in the blue area, a little wobbliness in x means nothing for y. So this is how we're going to describe error. We're going to say, error. We're going to want to say how much plus or minus something is. So what we're going to do is if we have a function, let me go back up here. If you have a function like x, let's say you have a cubic regression and you want to know how far off you are. That's the y value. That's how far off your y value is. That's just the derivative, the slope of the tangent line, times however far the x is. Okay, so we'll say y, the change in y is approximately equal to dy, which is equal to the derivative. This is dy is the differential, which is the derivative times dx. So all you have to do to find the error is find the derivative at some point, whatever it is, and then multiply it by how wobbly your data is. All of you have numbers, x values that are like 1, 2, 3. Yes? you all have numbers that are like that. You don't have like 1.1 or 1.05. Since you have numbers, you'll notice that for the worksheet in this topic, the worksheet is just, it just automatically says 0.5. Because if you're using whole numbers, well, 0.5 is the error. Okay? All right. Let me just show you on your project. So project error. So I just say y1. So you have the regression in there somewhere. And one of your columns is going, so you're going, y1 is your regression. So you're saying when I'm 72 inches tall, I should weigh 192 pounds. That's the prediction. Then y2 is just the derivative times 0.5. That's the error. So whatever the derivative is, you multiply it by 0.5 because my data was whole numbers. So this is saying plus or minus 3 pounds pretty much. So I should weigh 192 plus or minus 3 pounds or 2.8 pounds. Okay. And that represents this number here is just that divided by this times 100 is what's called the percent error. That's just a 1.5% error. Okay. So you understand what I'm saying? I'm saying I should weigh 192 pounds plus or minus 3 pounds because 72 inches, I might be a half inch off. You know, by the end of the day, I'm a little shorter. Did you know that? I know. And really, when you're older, my spine is like a sponge. When I wake up in the morning, I used to be 6'1". Oh, 6'1". Great. Now I'm lucky if I'm 6 foot. So I go to the doctor earlier in the day so that when he measures my height, I'm taller. Or I take a nap before I go. So I don't want him to tell me, you're 5'11" now. Because I know I am by the end of the day, I shrink. Could be. Yes, it could be. No, the percent error is just all this is here. Percent error is just how big it is the same. But what it is that 3 pounds is 1.5% of 192 pounds. That's all it is. So how far, because percent error is more important. If I was a baby and I weighed 8 pounds and you said plus or minus 2 pounds, that would be like 25% error. A baby weighing, it's the same amount of weight, the same plus or minus, it's just a baby is so small, it's a much bigger percent. Yes, it's the same percent error. People like percent errors better. People like error. And you know, politics, I hear it all the time. Within the margin of error. Okay. I know you've heard surveys that come out. I hate surveys because they're so done so poorly. But anyway, within the margin of error just means pretty much this, that the wobbliness of their X values is making their Y values off. So much so that they might not be predicting anything. Everyone's going to lose. Okay. All right. So you'll say in 1995, LG is worth 10 million plus or minus 0.5 million, which is a 0.005% error. All right, this is the end of this one. All right, back here. So we did inverses, differentials, and error. I'm just going to talk about these two, but I'm going to break us up. This is a good time to break up us into our groups. But the reason why I think we can zip over this topic is because, thank you, Desmos. This topic is a huge topic. It's one of my favorite topics. It's one of the real reasons calculus is interesting. What is 0 times infinity? Who have Naina? Are you there?
Yes,
Naina, what is 0 times anything?
0.
Uh,
0.
Yep, that's correct. Anusha, what is infinity times anything? Any positive number?
Infinity.
Okay, So you heard that. Infinity times anything is infinity, and 0 times anything is 0. Melanie. What is 0 times infinity? Now, one of them said 0 always, and the other one said infinity always. What do you say? I'm asking you because the answer is neither of them exactly. It could be 0, it could be infinity, or it could be anything. That's calculus. By the way, once you learn this, you are now welcomed into the, if you can get that correct, you are welcomed into the calculus club because that's what it's all about. You're not in it yet, but you will be. Of course. So I'm the founder of the calculus club now. Think about what I just said about fuzzy numbers. 0. If I said the number 0, Melanie, how far off am I? Plus or minus what? A half? A half times infinity is positive infinity. Minus a half times infinity is minus infinity. 0 times anything. 0 might be 0. We don't know. But anywhere, so your answer, it could be somewhere between minus infinity and infinity. And in math, when you don't know, you can't say it's anything. You can't be 0 or infinity. You have to say it's undefined unless you know more information. Okay, so if I keep cutting your grade in half, eventually your grade will go to what? 2. If I double your grade and I keep doubling it, what will eventually go to? If I take your grade and I double it and then cut it and then double it and cut it, one of them is doubling, that's going to infinity, and the other one's halving, that's going to 0. That's 0 times infinity. If I keep doing it, where's your grade going to go to? It just stays, right? It could be any number. So if you know more about how you're getting to infinity, the thing is about 0 and infinity, they aren't exact things. They're destinations. No, they're not destinations. You think they're destinations, but they're not. They're journeys. Do you understand what I'm saying? How much money do you have in your pocket? You think so?
Yeah.
If you multiplied whatever was in your pocket times infinity, you would have nothing? What if you had a crumb of gold in there? You'd be buried in gold. A flake of gold in your pocket would be more money than you could imagine if you multiplied by infinity. So you have to be careful. So anyway, you don't, so with 0 times infinity, it's L'Hopital's rule. Let me just quickly go to 0 times infinity could be anything. What you have to do is you have to do limits. Okay, and the L'Hopital rule only works with these things: 0 over 0 or infinity over infinity. 0 times infinity is a form of this, and there's other forms. And honestly, I can just skip right over this for now because all of these problems are not 0 times infinity. They're all the limits. And what can you do with limits? You can just use Desmos. If you want to know Desmos then. Where's Desmos here? If you want to know what 0 times infinity is, if I take the limit of x goes to 0. X is going to 0, right? Times 1 over x is going to infinity. You divide infinity by 0. So if you want to find the limit of x times x times 1 over x, put a minus 2 in there, whatever. It's the same thing. Anyway, oh no, that's not true. Anyway, if I want that, I can just ask Desmos to do it by just creating a function and plugging it in. I could just create a function of this. Okay, x times 1 over x. So if I want f of 3, the answer is 1. If I want to know what it is when I go to 0, it says undefined. But I don't put 0 in to get a limit. I put in what? 0.0 I just keep putting in smaller number, oh, look, not even get to this one. But no matter what I put in there, I get one. I'm getting closer and closer to 0, but I'm still getting 1. Okay, so we can always do that with Desmos, or you could have created a table. And if you create the table, you see that the answer is always 1 except at 0. So that's the answer. All right, let's get out of here. Let's get into our groups now and do the error problem. Yes, or the mean value. Let's do the error thing first. We'll go over the mean value thing next time. Even though the mean value thing is due today, maybe we should do the mean value thing. Now let's get in the mood. You guys did the mean value theorem last time? No, you're gonna go over it. Devon did the grade thing. Grade thing and what is this? Oh. This is the mean value theorem one. Okay. So he found the average rate of change is this. And the instantaneous rate of change. That's the average rate of change. Where's the instantaneous rate of change? There's the average rate of change and there's the instantaneous change. So the average and instantaneous are at the same at 13. All right, so what did you guys say? How did you say this? 13. Is there just, oh, Nana, how would you, could you read what you wrote here? So there's nobody here to read it.
According to the quartic regression, the average rate of change between 29 and 5 hours studying is equal to the instantaneous rate of change at 13.064% per hour studying.
Not what I'm reading here. First of all, change this to 5 and 29. 29 and 5 is backwards. Nobody says between the ages of 50 and 25, right? When I was between the ages of 50 and 25, no, it was when I was between the ages of 25 and 50. So switch them. And the instantaneous rate of change is the same at, oh, you changed it to, no, it's not 13%, it's 13, it's the same, it's equal to the instantaneous rate at 13 hours of studying. So get rid of those decimals because mom doesn't want them. And just say hours of studying, no per. Got it, Nina? Can you fix that?
Yes.
Good. Next post. Kara. Wait, hold on, let me go find two. Melanie. Melanie, you're also the studying one? Uh-oh. But it's the same. Uh-oh. You guys picked the same points, 5 and 25. Did she say 29?
Yeah.
Oh, okay. This is 5 and 25? Okay. Sarah, you want to say what this says? According to... Oh.
But I have it on my computer, but it should be said. Can you say that?
Just say it out loud what it should be said. Say it loud though so they can hear you at home.
According to the quartic regression, the average rate of change between 5 and 25 is equal to the instantaneous rate of change at 13.31, or I guess at 13 per hour.
Not per 13 hours of study. You're studying for 13 hours. At 13 hours, you're picking up grades at the same percentage as you are percent per hour. You're picking up the same, which is, no, see, this is written wrong. Who wrote this? Jacob, did you write this? Let me tell you what if you want to fix this, and you should, you need to do the following. you need to write F prime of that. Okay, this right here is the average rate of change, the arc. This one has to be the instantaneous rate of change. That's what the mean value theorem says. Okay, so just put a F prime there. And you're good. Okay. Any questions on that? Why do I? Okay. Let's go back to this post. Kara's doing BFFs and Sally. I see nice parallel lines. So what's going on here? What are you going to say? Nobody's saying anything. Kara, who's in your group? Why didn't they say anything? Oh, we're here. Are you here?
Yes.
Okay. So you're going to fix this? So you say something? Anusha and Suhabi, they're both there. So she posted it.
So
And
what happened was that Anusha wasn't here last time, so she didn't know what she had to do, but we said that she was gonna do like the writing portion and I was gonna do the speaking portion. But she just wasn't here last class, so we had no way to tell her.
Yeah,
Okay.
I was like sick last time, so I didn't come, but I'll like do it today and then like we'll finish ours today.
Okay, good. So you're gonna do the writing. Anusha's doing the writing. Suhabi's doing the speaking. Well, someone's gonna say something out loud so I can play it.
Yeah.
So either the speaker or read just whatever all you have to do is read out what they have, what they write. But somebody has to write it first, or you can't do it. Okay. Let's get into our groups then and do the next one. Do you need me to show you what to do for the next one? Because it's not that bad. You're going into lessons. Oh, it's not available to you, but it's available to me. Okay, example worksheet. So you have the worksheet still, right? It's all done. There's nothing to do here. Except go to error and look at it. It's already done. I didn't do anything. I just opened it. There's your producer thing. There's no graph required for error. Maybe it would be nice if you're going to use a quartic regression, maybe turn the quartic one on, but that would be up here, I guess. Okay, so I turn that on, and then I produce this chart. But the only thing you might have to do is decide on whatever values you want. This is A1, B1. Pick a value. So for me, this is about time and distance traveled. So if I say 12 hours, get rid of these. So at 12 hours, so I have f of 12 is approximately equal to 6.656 plus or minus the 12. And then it says percent error equals 1.83. Then what's the speaker going to say? According to the quartic regression, after 12 hours, we have traveled 656 miles plus or minus 12 miles. That represents less than a 2% error. Make sure you don't make none of these numbers are negative. They're all positive. Because you put that plus or minus, one could be negative. The first one could be negative. So if you're doing BFFs, though, pick one that has positive BFFs. Don't pick one of those negative ones. Okay? Not too hard. It's already set up. Just have to figure out who writes and who does that. All right, let's break up into our groups. Breakout rooms. We have 2 breakout rooms, yes. So breakout room 1 is Kara, Nyla. No, you're not. No, oh. The business group. Who is in the business group? I don't know. Let me see. I know Devon is in that group. I know.
Devon isn't in our group.
No,
It's me, Suhabi, Anusha, and Mihir.
Okay, you're all at home.
Isn't Mahir with you in class?
Who are you looking for?
Is Mahir in class?
Yes, he's here. We're here,
Okay.
join, so you can talk to your group. Okay, so that room is open and you three have people. You have people, yep. So half your group is home. But you're gonna join in room 2. Somebody. What? Oh, okay. Right. You guys are talking
Did you post it?
to postpone. No, I'll do that right now. You mean mod 6 is still closed? If that's what you're asking. First, I have to open up mod 6.
Yeah, so it's just planning on like looking at what the other group did and like, you know, like figuring it out from there. Okay, yeah, that's probably good. Yeah, okay. So I'm doing like the writing words, right? But not the math, or am I trying to?
Yeah, so would you, yes, supposed to, it's the process of something.
I'm doodling, thank you. No. It's error. It's error.
Did he say do that this week?
Mean value theorem, finish that first. Tell her to finish mean value theorem first. It's almost, hold on. All right, hold on, I got it, it's done now. Tell her to look now. It's up now.
So you guys will be close. Something else from here. So I'm not gonna lie, probably not gonna get to the say. I think you all the more options to speak to you, and then you can just speak it down. Yeah.
So, guys, did you guys finish the mod 5 writing?
Do you think that we posted, you could, produce two, like, different, perhaps, like, so one with one set of points and then another one was the same thing, just like a different set of points?
Like, for error? Just produce, put another thing on the table.
Like different,
You just put 3 or 4 of them on the table, we have plenty of things that everyone can say, just make sure somebody says something.
No.
I keep forgetting your group is big. Okay.
You check the, distribution just, published it.
Professor,
Yes.
wondering if you could take a look um at our MVT discussion because like our percent value is like a little like high.
It could be. What do you say? What's how high is high?
It's like 138.
Okay, it could be. Hold on, let me see.
Okay.
Lesson. 6.
Yeah, the ones basically, for one, and then for the other one. Like which one do you go?
Okay, so you want me to look at mod 5? Where the average where the
Yes.
mean value theorem is. And you want me to look at
So,
Kara's? It's you,
Yeah, it's under Karis.
okay?
but I'm just gonna like.
Wait, this is the error, right? You guys are gonna finish this one first. The error is, that's something else. You want me to look, did you give me the link here? I can just check the link. So for the error one, if you're talking error one, which, okay, look, it depends on which salary you're talking about. If you're talking about a salary here where the derivative is kind of flat, the error will be very small. But if you're talking about one of these salaries where the derivative is really steep, then the error is going to be very big. Which one are you using? What point are you putting in? Pick a number, any number.
Wait,
For-
but I thought the error one was for mod 6.
It is for mod 6, but you just had mentioned error, so I thought you meant this.
No, like I meant to publish it for like the percent in between like the two values.
The average rate of change one?
Yeah.
You mean value theorem one. Okay, so let's go into mod 5. Okay, and what am I looking for here? I'm just not sure. What am I looking for?
Yeah, that was the wait, that should be like the same one that you were just at, I'm pretty sure. But
No, but this is the thing. No, it's different because this is the average rate of change is between 100 and 200. So if your average rate of change between 100,000, which is this salary, and 200,000, which is way down there, that's pretty big. But this the slope is minus 0.135. It's a small number. Oh, because the number of friends are small. Look, this is thousands of dollars here, and these are friends. So that number isn't going to be very big. That's fine. And then it says 138,000. It's right about, must be right there. Okay.
okay.
So that's fine. So according to the two-quarter regression, the average rate of change between $100,000 and $200,000 is about the same as when you're making $138,000. At the instant $138,000. So in other words, a person who's making $138,000 is losing friends at 0.135 friends per $1,000.
Oh, okay. Okay, I think I understand now.
But the average is in that whole region, on average, if you went from 100,000 to 200,000, you'd lose 0.135 friends per 1,000.
Okay, that makes sense. Thank you.
No problem, Richard. Good luck.
So. If you guys want to bring to I'm changing one word. So it's just like it's
You guys okay over there? You're awfully quiet. You're okay? Okay, let me see who's here today. Oh, we have 3 minutes. Finish up.
Put the quotations on. Like, if you don't want to, like, if you're writing.
Just either you can do it 2 ways. You can either just go up here and say add a quotation mark, or the way I do it, I literally go to blank line and I hit the quotation marks and it automatically does that. Pretty cool, huh? Okay. I need to take attendance, so we're going to ask these questions today. All right. Two hobbies here, Nyla's here, Sarah's here, Jacob's here, Damon's here, Kara's here, Mahir's here, and Anusha's here, Melanie's here. Everyone's here. Just leave it at that. I'm gonna close breakout rooms. So you have a minute. What happened to your room, Mahir? Are they still there?
I think they left.
They left? Before knowing whether I took attendance or not? The breakout room is closing in 39 seconds. It's okay, they'll be in the regular room. How you doing, Melanie? Did you do okay on that test? You want to talk to me about it? Are you okay? I don't remember. Okay. I'm gonna make it so that the grades, they give you feedback, but I definitely made notes on tests here and there. Some people lost points for things that they're not gonna be happy about, because I wasn't happy. Like, again, typing before you say something was a no-no. Okay, so the derivatives test, you want me to okay, so show test description to students before they begin the test. Okay. Test instructions. Show instructions to students before they begin the test. Okay. Okay, so what do you want? You want to say all answers? Oh, is today the 11th? Oh, no. I'm just going to say after submission. So now it's going to show you everything. You all took the test. I'm not giving any makeup tests in this class. Y'all making me happy. Even if you didn't do well, I don't remember who didn't do well, but look at the answers and you'll just do better next time. Okay? Take care. Have a good day. All right, you guys at home, I took attendance, so you can leave.